Here's the basic ideas of the hypothesis test, and it applies to z distributions, t distributions, chi-square distributions, f distributions, all of them. Just to keep things simple, let's just stick with with the z distribution. Okay, so you have your distribution, and every hypothesis test has two hypotheses, two opposing hypotheses. Okay. One is called H sub 0. That is known as the null hypothesis. And the other one is H1. That is known as the alternative hypothesis. Okay, and that's just what they're called. Okay, now whatever variable, or well, more specifically, whatever parameter, like mu, sigma, sigma squared, p, something like that, whatever the parameters that you're making inferences about, that parameter goes in the hypotheses. Well, let's just stick with the basics. Let's just say that we want to test a hypothesis about the mean of a population. So mu, the mean, is the parameter that would go in the hypotheses. Okay, and if it goes in one of the hypotheses, it goes in both. So it's not like you're ever going to mix and match. Now, let's say that in the problem, the hypothesis says, or there's a hypothesis in there that says something like this. Test the claim that the mean number of pineapples is more than 25. Okay, and the wording of that statement, as I have it, is fairly typical of how they'll look, on tests and in the homework. Well, I see the word mean, so I say, okay, mu, that's my parameter that I'm interested in. I see test, I also see claim. Either one of those words lets me know, oh, this is a hypothesis test, not a confidence interval. Right. So I'm doing a hypothesis test. So I'm doing HO and H1, null and alternative. I see the word mean, so I know I'm going to have the mu right there. Okay. So now what do? Well, it says that the mean number of pineapples is more than 25. So the question is, do I put mean is more than 25 there? Or do I put mean is more than 25 there? Turns out that it goes in the alternative hypothesis. Okay. Since there's no equal sign in this statement, whoops, didn't mean to do that. Since there's no equal sign in the statement, like mu is greater than or equal, okay, there's no equal sign. That means it goes in the alternative. So the alternative hypothesis always contains the statement that does not have an equal sign. And by default, the null hypothesis always does have an equal sign. Okay, again, same parameter, mu, and it'll always have the same number, in this case 25. And it always has an equal sign every time. Okay, so H1, the alternative hypothesis, never has the equal sign. HO, the null hypothesis, always has an equal sign. Now, depending on the wording of the problem, in this case it was more than, depending on the wording, H1 might, we might have had something like this. What if it was less than 25? Okay, then we would stick a less than sign there instead of the greater than sign. Or what if it looked like this? What if it says test the claim that the mean number of pineapples is not 25 or is different from 25? Okay, then in that case, you would put a not equal sign in there. Okay, so the alternative hypothesis always has a less than or a greater than or a not equal, always. Okay, so setting up the hypotheses, that's an important thing. Okay, because you have to get it right. Otherwise, you've set up a bad foundation for yourself, and you're just not going to get the right answer for the problem. Okay, and here's why. First of all, if you have to get the right parameter there. Okay, if you put a mu there when it should be a sigma or it should be a p or something else, then you're going to go to the wrong formula. So you've got to have the right parameter there. Okay. Secondly, you have to have the right symbol there in the alternative hypothesis, because that tells you about the tails in the drawing for your that represents your situation. Here's what I mean. If I have a less than sign, I'm sorry, a not equal sign. Not equal means, well, like I've got it right here, Testacland, the mean number of pineapples is not 25, meaning that the number of pineapples, well, it's either less than 25 or it's greater. It's one or the other. I'm not sure which. Okay, so in that case, when you have a not equal sign there, it means you have less than 25 or greater than 25, one or the other. Okay, you have what we call a two-tail situation. And visually, it looks a lot like the confidence interval. So when you have the not equal sign, you got two tails. Okay, well, what if we don't have a not equal sign there? Okay, what if we have something like greater than? Had it been a greater than sign, greater means go to where things are greater. Okay, on the right side, just like on a number line. Go to the greater sign. And then we have a one-tailed situation, and more specifically, a right-tailed situation. Now, what if we have something like less than? Less than means we got a left-tailed situation. Okay. Now, if you're a little confused about what the tails mean, that's fine, because I have not yet explained, so it's okay. I'm just kind of giving you some of the basics, though, right up front. All right, so now let's break down the anatomy of the drawing. Okay, whether it's one-tailed or two-tailed, you're going to have a shaded region and a non-shaded region. Okay. The shaded region, that basically corresponds to H1. And the non-shaded region essentially corresponds to HO. Okay. So you have the shaded region, that's the H1 region. The non-shaded region, that's the HO region. The H1 region is typically referred to as the critical region. And you'll see that in the textbook. That's called the critical region. Now, there's two ways to determine. Well, I'm getting just a little bit ahead of myself. Okay, so in a hypothesis test, essentially, I'm not going to say it perfectly well. I'll save that for class. But essentially, what you want to do is just follow the hypothesis test procedure and then decide, am I going to go with HO as my solution? The mean is 25. 25 pineapples, or am I going to go with H1? The mean is less than 25 pineapples. Okay. And then whichever one you go with, well, that's basically your answer. And then you'll write it up kind of like we did with confidence intervals. So now there's another thing there are two ways to proceed at this point. One way is the critical value method. And what that means is you have a special formula, and your calculator finds it for you, but you have a special formula, and that formula gives you the critical value. The critical value is a number, okay? And that number is either going to be on this number line here, that number is either going to put you over here in the critical region, the H1 region, or it's going to put you over here in the null hypothesis region, the HO region. Okay. So if it goes over here, then our test value, our critical value, ended up in the critical region, ended up in the H1 region, suggesting we believe H1 is the answer. That makes sense. Or if the critical value ends up over here in the HO region, then we assume that HO is the answer. Okay. So that's the idea. So that's one way to do it, the critical value way of doing it. Oh, and incidentally, this number right here, okay, that separates the critical region from the non-critical region, that is called, oh, whoops, okay. Sorry, I was getting ahead of myself. I'm sorry. Okay, this guy right here, this is the critical, that's the critical value. Sorry about that. The number that ends up over here or over here, that's called the test statistic. Sorry. Okay. So that's one way of doing it. You just go find the test statistic, see if it ends up in the critical region, the H1 region or the HO region, and you go with the corresponding hypothesis. Now, a different way of doing it, and the way I'm going to do it in class, because, well, ultimately it's going to be easier, is to use what's called the p-value method. Okay, p-value. Okay. And what the p-value method does is it does the same thing, but it kind of approaches it from just a different point of view. Okay. For example, in the picture we've got here, the critical region, the shaded region, has a certain amount of area shaded. Let's say that it's about 5% of the area under the curve, and that's quite typical. Now let's say that we find our test statistic, and it is right there. Okay, there's our test statistic. Now the amount of area from the critical value, actually I should probably label that a little better. The amount of area from the critical value out to the end of the tail is 5%. Okay. So what would be the area of the test from the test statistic to the end of the tail? Would it be more or less than 5%? Well, it'd be more. Okay. Now that area that I have in, I'm colorblind, it's either blue or purple. Okay. That area there is called the, we refer to it as the p-value. That amount of area, that is the p-value. So in this case, maybe the p-value is 0.065. I know it's getting messy. Isn't that wonderful? Okay. So the p-value is about 0.065. So, well, I can tell from the picture that the test statistic ended up in the HO region. Okay, but if I think about the those percents, the 0.05 and the 0.065, okay, then I can tell that when the p-value, whoops, my pen didn't write, when the p-value is greater than the amount of area in the critical region, which we refer to as alpha, okay, when the p-value is greater than alpha, when the blue is greater than that green or orange or whatever that is in the critical region, then that means the test statistic is in the HO region, in which case we go with HO. However, if that test statistic, if it were not to the right of the critical value, but if it were over here to the left of it, then the amount of area from that guy to the end of the tail would now be smaller. The p-value would be smaller, okay, than the 0.05, than the amount of area in the critical region. Okay, suggesting that the test statistic is now in the critical region, is now in the H1 region, in which case we go with H1 as our solution. Okay, just don't worry, it's not as hard as it sounds, but it does take some getting used to. But if you work at it hard, you will get it, and you'll get it pretty fast.